This is an introduction to VLSI design course, and now we will talk about the SRAM. So we will talk about the memory array in general, and then we will specify the SRAM, where we will talk about the SRAM cell, the decoder, the column circuitry, and all that will end up with the other type actually of the memory arrays, which is the serial access memory. So let's begin with the memory arrays. In the memory arrays, we have the random access memory, the serial access memory, and the content addressable memory, or what is called CAM. The focus here is on the random access memory and the serial access memory. So the random access memory have the read-write memory, or what we call the RAM, which is usually volatile. And the other type is the read-only memory, which is the ROM, and usually this is non-volatile. Now, for the RAM, we have the static RAM, the SRAM, and this is the focus of this video. And we also have the dynamic RAM, or what we call the DRAM. For the ROM, we have we started historically speaking with the mask ROM, and then after a while we have the programmable ROM or the PROM, then the erasable programmable ROM or the EPROM, and then they modify to make it electrically erasable programmable ROM or the EEPROM, and after a while we introduce it, or we introduced the flash ROM. Now for the serial access memory, we have the shift register and the queues. The shift registers, there are actually 4 types. We will talk about 2, or we will focus on 2 of them, the serial in parallel out and the parallel in serial out, or we can call this one the SIPO and this one the PISO. The other 2 types is actually the serial in serial out and the parallel in parallel out. For the queues, we have the FIFO and LIFO, the FIFO being the first in first out, or usually we call this the queue. It has 2 operations, the in queue and the DQ. And this one, you usually call it the LIFO, the last in first out. This is the stack. And usually we do the push and pop operation. So in this video, we will focus on the SRAM and the SIPO and the PISO, and also the FIFO and the LIFO. So the memory terminologies in general, we have usually a DIMM, or the dual inline memory module. This is what you see if you open the case of your PC or the back cover of your laptop. This DIMM, this example, is actually a 2 GB DDR3 dual inline memory module. It has 2 ranks or 2 sides. The first rank that you see in the slide, and there is another rank in the back. Now, each chip that you see, and the black chips, we have 8 in the first rank, and we have 8 more in the second rank or in the back rank. So if we take the first chip in the front rank, the 128 megabyte chip, we can see the details for it here. And you can see that it consists of 8 different banks. Each bank is responsible to give you a single bit. This way, you get a bit from here, a bit from here, and you accumulate the bits until you get a single byte. This is why it is, for a bank, it's 16,384 times 1,024. That's the choice that they made for this bank. And now we make it in design. We distribute it between rows and columns. And we would love to make this shape as square as possible. So we have the row decoder. We have also the column decoder. So this way, if we want to see what's going on here, so we will have 16,000 rows here, and we will have 1,000 column. I'm trying to approximate you. So once you can, using those these two decoders, you can pinpoint a cell. So in the decoder, it will make one of these line equal to 1, which is this line. This line will be equal to 1 based on the address that you are given in the raw decoder. This will be 1 and the other lines will be 0. Similarly, this one will be 1 and the other lines will be 0. And this way you picked a single cell. This cell in this example is actually a dynamic RAM or a DRAM cell, where it is composed of a single transistor, an NMOS transistor, that is feeding a storage capacitor. And the value logic 0 and logic 1 is what is stored in the capacitor. So if the capacitor is full, it's a logic 1. If the capacitor is empty, it's a logic 0. Now let's see how did we get the 2 gigabyte. So as we said, this chip is 128 megabyte chip, and we have 8 in the front rank plus 8 in the back rank. So in total we have 2 gigabyte DIMM, and you can get this result by saying that this is 2 to the power of 7. That's that 128. And 8 plus 8 is 16, and that's 2 to the power of 4. So 4 and 7 is 11, and we have 2 to the power of 11 times megabyte, which is 2 to the power of 20. If you add those two, you will have 31, which is basically a 2 gigabyte. Now, the 128 is organized and within banks as 16K times 1K, and we have 8 banks. This is why we have 16 and 1K, and we have 8 different banks. That's basically the memory technologies, and I believe now you understand what's going on when you see this DIMM. We also have some buffers that helps speed up the read and write operation. So now for the array architecture, now we will focus on this part here. Basically, the whole thing. We will focus on this part. So in the array architecture, we have a row decoder, and we have what we call a column circuitry. The column circuitry here is just simple multiplexer. Sometimes it's only buffers. Now, as you can see, this is a rectangular shape, and we don't like this. So we make it as square as possible by folding. So we take this part in the top and we fold it right here. And now we have a row decoder. And because of this folding, we will also have a column decoder with multiplexers at the end. To understand this picture clearly, so as I said, we have a row decoder, we have a column circuitry, and we have word lines. This word line will be 1 if you choose a certain word. So if we choose this one, we will have 1 all over this, and we have 1 for those 4 cells. Now you can pinpoint one of the cells by choosing its column. Now we have also the bitline conditioning. The bitline conditioning is just preparing the cell for read and write, and we will talk about it in a few slides. Now, again, we have the bitline conditioning here. We have the row decoder. Now we have the column decoder as well. So if you have 2n words of 2m bits each, if n is much larger than m, you fold by 2 to the power of k into fewer rows. So this is n, and you have 2 to the power of m as an output data. And if this is a rectangular, it's too much. N is much larger than m. If that's the case, like in this example, n is actually 4. So the output of the decoder will be 16 lines. And the data that you want for this memory is 2 to the power of 2, which is 4. So as you can see, this is 16 and this is only 4. So what you do, you fold. Now, when you fold, you're actually taking some of the row decoder and make it into column decoder. So basically this 4, we distributed it to 3 and 1 by introducing this k. So k here is equal to 1. 4 minus 1 is 3, and the k will be over here. And now we have a square shape. This is to have fewer rows and more columns this way. It will become good regularity, easy design. A very high density of good cells are used. You can do it like repeated over and over. Now, the question for this design, what we want is 4 words. 2 to the power of m, which is equal to 2 to the power of 2. So m is equal to 2. And the number of bits in the output is 4 bits. And this is actually what we have in the original design. We have 4 bits coming from each word. So if I choose this word, if I choose this row, so you will get 4 bits here and here and here and here, and you generate them directly into the output, so you can have buffers here. If you fold it and put it there, now you will have 2 columns for each output. So you need a multiplexer to choose from these 2 columns. Also here and here. And so you can see now you had only 4 columns, and now we have 8 columns, and we need to convert these 8 columns into 4 output lines by taking each 2 and generating 1 from them. And that's actually setting your multiplexer size. The multiplexer size, or the T in the multiplexer, is actually the number of columns divided by the number of outputs. So it's basically 8 divided by 4 in this example, and that's equal to 2. Now, to understand this better and giving you more realistic example, as we said, the array may be folded for good aspect ratio to make it square-like. If we have a 2k word times 16 times 16, and that will show you the naming of the memory. Now, this will give you an information about the address or the decoders, and this will give you an information about the output. You can look at it in a different way, that this will be an information related to input. This will be information related to the output. So we will fold this into 256 rows and 128 columns. The way we did that is actually 2 to the power 11, since we said 2k words. So that's 2 to the power of 11 times 2 to the power of 4, since we said that the output is 16 outputs. Now, if you multiply both of them, you'll add the exponents. So 11 and 4 is 15. Now, you make it as square as possible by dividing the total by 2. So now this is 15. You can divide it into 8 and 7. We chose that to make 2 to the power of 8 rows, and that's 256, and 2 to the 7 columns, and that's 128. Now we must select 16 outputs, since we said it is actually 16 bits. And we have 2 to the power of 7 columns, which is 128 columns. So the multiplexer will be 128 divided by 16, which is equal to 8. So the multiplexer here is 8 to 1. And the address line, since we have 2 to the power of k word, the address line is actually will be 15, since when we multiply those 2 together, we had 2 to the power of 15. So we have 15, and we distributed it to 8 and 7, as we mentioned. And the mux size now is 8 to 1. And the data at the output, the one that we want, is 16, so it's 2 to the power of 4. Now, after checking this array, now we will focus on each part of the array. We will talk about the cell. We will talk about the decoders. We will talk about the multiplexers, and we will also talk about the bit line condition, starting by talking about the cell itself. So there is many designs. One design is the 12 transistor SRAM cell. It's actually a basic building block for the SRAM cell. You hold one bit of information like latch. And as you can see, we talked about the latch design before, and that's what's exactly what we do for the SRAM. We make it like a latch. So you hold one bit of information like a latch, and it must be read and written. As you can see, we have write bar, read, and read bar, because you have actually the value and you have the opposite of the value for this two inverters that works like back to back. The 12 transistor SRAM cell, it's use a simple latch connected to the bit line, as you can see here. And the unit cell, in terms of area, you can design it like this. And it will be 46 times 75 lambda. That's the 12 transistor cell, SRAM cell. The more important one, and the one that we will discuss thoroughly, is the 6 transistor SRAM cell. And as you can see, it's basically two inverters back to back, followed by two NMOSes that are controlled by the word line. So if you choose this cell, this word line should be activated or equal to 1. Once it is equal to 1, this will be on and this will be on, and now you can read and write the content of the cell. So the cell size account for most of the array size, as we have seen. We reduce the cell size to 6 transistors coming from the 12 transistor. The 6 transistors SRAM cell used in most commercial chips nowadays. The data stored in cross-coupled inverter, as you can see here. Now, how to perform the read and write? Now, you have to focus with me, because maybe this information will be surprising to you. Now, we have two vertical lines. We call it the bit and the bit bar. As you can see here, we redraw it over there as two inverters back to back. You can see that the input is connected to the output, and this input is connected to this output. Now, we have for bit and bit bar 4 possible options. Either the bit and bit bar is going to be 0, 1, and 1, 0, or 1, 0, and that's what we expect, because we named it actually bit and bit bar. So I have the value here. If it is in bit bar, then the opposite of it will be in bit. So if it is 0 and 1, we look at the bit. If it is 0, 1, then we are reading or writing a 0. If it is 1 and then 0, then you are reading or writing a logic 1. In case of 0, 0, and 1, 0, 0, we will never allow it. So it is not allowed. And we will make sure that this two vertical lines, will never have a 0 and 0. The 1, 1, if you have 1 here and 1 here, then this means that you are pre-charging the lines. So the lines will be pre-charged at one time and evaluated at another time. And we talked about this when we talked about the dynamic logic, the domino, and so on. So in the read, the operation of the read, we pre-charge bit and bit bar first. So we make them 1 and then 1. And then we raise the word line, meaning that we select this cell, and then the read operation happens. For the write, we drive the data into bit and bit bar. So we want to write into the cell. So we make the bit and the bit bar based on the value that we want to write, and then we raise the word line. Now, this is the general read or write. We will talk about the read in details, followed by the write. So what happens in the read first? In the SRAM read, we do these 3 operations. First, we pre-charge both bit lines, which means bit and bit bar. And then we turn on the word line, this word line. And then the effect of this, one of the two bit lines will be pulled down by the cell. To understand this better, look at these two scenarios. If we want to read a 0, if you want to read 1. So let's suppose that we want to start with this one. So we want to read 1. The steps that we will make is those 3 steps. First, we will pull the bit and bit bar to make it 1 and 1. And that's what we had. The bit have 1, the bit bar have 1. And then we will make, or we will pull up the word line, we will activate it. We make it equal to 1. Now, in this case, there was a 0 and 1 within the cell. So you have 1, that's close to bit, and we have 0 close to bit bar. So in our case, if A and A bar, now A and A bar is with what's inside the cell. We call it A and A bar. If A and A bar is equal to 0 and 1, what happens? We must make sure that this 0 overcome this 1. So the read operation of this 1 happens. How? Like this. Like this. The 0 will overcome the 1 and it will become 0 in the bit bar. Now, for this to happen, let's see where is this 0 coming from and where is the original 1 coming from. So this 0 is coming actually from the pull down here, which means it will pass through N3. While the 1, you have no idea actually, because this is a best transistor. Either the 0 will go this way or the 1 go this way. So it could be this way or that way. Now here the 0 is coming here. The 1, it will fight the 0, let's say, through info. To make sure that the 0 overcome the 1, we make N3 much bigger than N4. The width of N3 should be much bigger than N4. This way we make it strong, and this one is a little bit or weaker than the N3. And this is why we have N3 much larger than N4. Now for the case of reading a 0, meaning A is 0 and A bar is 1. We do the same in 1 and 2. Now 3 is different because the value is actually different. Now we want this 0 to overcome this one. And this could happen like this, where you have the 0 here. And again, with the same mentality, we must make sure that N1 is, which is this one here, is much larger than N2. So basically we covered the read operation. Again, we pull both lines to 1 and 1, and then based on the value inside, one of these lines will become 0. And for reading the 1, this line will become 0. For reading a 0, this line will become actually 0. To make sure that this is what happens, we make the transistors or the NMOS transistors at the pull down much larger than the transistors or the NMOS transistors that are connected to the word line. Okay, so let's check now. After covering the read, we will cover the write. So in the write, we have 3 steps again. We drive one bit line high and the other low. So it's either we will write a 0 or a 1. If you want to write a 0, you make the, if you want to write a 1, you make the bit 1 and the bit bar 0. If you want to write a 0, you make the bit 0 and the bit bar 1. So that's what we do in the first step. The second step, turn on the word line, make the word line activated. Now the third step, the bit line overpower what's inside the cell to make sure that you are actually writing inside the cell. How is this happening? We will have 4 different scenarios. The first scenario is this one. Let me cover these two first. So in this scenario and this scenario, what happens in right to one, A and A bar is equal to 0 and 1. So you have 0 and you have 1 here. And you want to, inside the cell, that was the previous value, 0 and 1. And the bit bar that you want to write is also the same. So the bit is equal to 1 and bit bar is also equal to 0. So basically, once you open the word line, open these two in MOSes, the 1 will go to the 1 and the 0 will go to the 0. There is no need to overcome. So the right operation will happen. Actually, basically, you've done nothing because the value that you want to write is matching what's inside the cell. Writing a 0, now you have 0 and 1, and what's inside the cell is also matching what you want to write, so it's also 0 and 1. If that's the case, there is no overcoming here, so everything works fine. Now, let's see what will happen if there is if the value of the cell is different than what's in bit and bit 1. So in this example, we are trying to write a 1. You have 1 in bit. You have 0 in bit bar, and what's inside the cell, A is equal to 0 and A bar is equal to 1. Now what happens, we want again, we will do the same as the read. We want the 0 to overcome the 1. So in the SRAM, always we are looking for this property. We want the 0 to overcome the 1. So for example here, if you have a 0 and you have a 1, let me go back one step. So if you have a 0 and you have a 1, sorry, the animation is. So as you can see here, if you have a 0 and you have a 1, you have a 0 here and you have a 1. You have also, so this 0 should overcome the 1, as you can see here. So the 0 will overcome the 1, and then it will happen to the other value by the inversion. So this 0 overcome this 1, it replaces value, now it's 0. And by inversion, the back-to-back inversion, this 0 will become 1. And this way you change the value inside this. That's if you want to write as 0. Now, if you want to write the 1, again, the 0 should overcome the 1. So this is what will happen. The 0 will overcome the 1, and then you will change the value of the cell by the back-to-back inversion. That's basically the right operation. Now, to make sure that this is correct, and this is always what's going on, or what will happen, and not the other way around, to make sure that the 0 is overcoming the 1, and not the 1 overcoming the 0, you have to make sure that the path of the 0 is stronger than the path of the 1. The path of the 1 is actually the PMOS. So let me go one step before. The path of the 1 here, this one, is actually coming from the PMOS. So we make this one, or the N4, larger than the P2. Similarly, we make the N2 much larger than the P1. Or basically, we make the NMOSes that are connected to the word line much larger than the pull-up PMOS transistor of the 2 inverter for the right to work. So now we have the properties of the read and the write, and we can combine all of them together like this, where we make these 2 transistors very large, and these ones, we make these 2 very large, and we make these 2 medium, and these one or these two, very small. So large, medium, and small. You can say it as strong, medium, and weak. If you do the sizing of the SRAM this way, you made sure that the read operation and the write operation works nicely or works correctly. Now, how to make sure that the first step is correct? Now, when we talked about the read and write, the first step was pre-charging both bit line and bit lines and making them high for the read. Similarly, for the write, we said drive one bit line high and the other low. So we must make sure that one of these bit line is high. How to make sure of this? To do this, we will have the bit line condition. And the bit line conditioning, we actually have seen this before when we talked about the dynamic circuits, the domino and the dual rail domino and so on. So now we have the SRAM cell that will work when phi1 is high. So we have the evaluate here. And in phi2, when it is high, we will have the pre-charge. So in phi2, when it's active, this transistor will be on, the PMOS transistor will be on, and this one also will be on, or will be on. Both transistors will be on, so the VDD will be connected to the bit. This is the bit, and the bit bar. So at the beginning, in the read, you will have 1 and 1. And now that's the first step of the read because of the bit line condition. And then if you want to read, the next side, or when phi1 is active, so in phi2, you pre-charge, you make them 1 and 1. In phi1, the read operation will happen, and you will have the value in bit and bit bar. We have two inverters at the end, and we call now output and output bar. We call the output of these two inverters. So the output will be for the this label, which is out, is the output of the bit bar line, and this label out underscore B is the output of the inverter, or this vertical line, which is bit. Anyway, we added these in two inverters to protect actually the cell from any possible noise, whether the charge sharing, like if this inverter wasn't there, or these two inverters wasn't there, if there is a value here, like a VDD or 5 volt, and you is fanning out to so many cells, maybe it will lose its value. So to make sure that it doesn't affect the inside this SRAM cell, we protect it by two inverters. Also notice that all the calculation where you raise the word line, the value of the bit or the output, it's all happening within the evaluate session or when phi1 is active. This is why you see the naming V1 and V1F and so on. Also the Q1, because they are all working on phi1. V1 for valid signal, and Q because it's usually the word line is gated by an AND or NAND. Okay, for the write, now the write is very similar to the read. You have the bit line conditioning. So at the beginning, you have 1 and 1. And the first step of the write, you must make sure that one line is 1 and the other is 0 based on what you want to write. So you activate the write signal, meaning that I'm going to write. So you have two transistors here. If the write is equal to 1, meaning that this transistor is on and this one is on, so you can write into bit and bit bar vertical lines. The way you write is you have a data that you want to write. This data will go to this gate as normal polarity, and here it will be inverted. So one of these transistors, the two bottom NMOS transistor, one of them will be on and the other will be off based on the value of the data. If one of them, let's say that this one is on. If this one is on, meaning that you're having the value here equal to 1. So here is 1, and this transistor is on, and here is 0, and this transistor is. Now the value that will go to the bit line is actually 0. This is the ground, and the value that was 1, 1 in phi 2, when you evaluate, when you get the data value, and the type of it is this for stable, when you have this data value, it will be both the value here that was the beginning when in phi 2 was 1, 1. This one will be replaced by this. And now you have a 0 and 1 if you want to write 1. So you have a bit 0 and a bit bar 1. If you want the other way around, you will have a 0. So this will be 0. This will be 1. This was off. This is on. So the 1, 1 in the pre-charge stage, one of them will be 0, which is this one, because this will be on and the 0 will be connected. So this way, the read and write will work. Of course, we need to combine both of them together, and we will see this at a future slide. This is the layout. You can see that you have the ground. You have a ground here, and you have a second ground. You have the VDD horizontal. You have the bit and bit bar, and you can see the inverter back to back right here. And you have the word line here. This is the word line, and you have the transistors. You can see the diffusion with the poly, the diffusion with the poly. Also here we have the diffusion with the poly. This is the diffusion, this is the poly. You have the diffusion here. This is the diffusion, and this is the poly. Also the PMOS as well. So to understand this better, because the layout, you might not see the details. In stick diagram, this is the way you do the stick diagram. You can see the PMOS is right there. The PMOS is right there of the inverters, the two inverters back to back. And this is the NMOS, and this is the NMOS. And you can see the crossing here in the word line. You have another two transistors right there, which will be here for the two NMOS transistor connected to the word line. And you can repeatedly have more cells this way. So we copy this cell exactly here. You can see that this is shown here, exactly just shift it over there. And we did the same here. Just move it and shift it right there. And once you have the appropriate number of cells that you want, you flip everything upside down in the bottom. And so on. You keep doing this. Once you have 4 of them, you can copy and paste it however many times. Now, there is actually a small problem with this one. As you can see, the details are here. This is the size. And you can see that we are doing the ground and the VDD. The ground is vertical. The VDD horizontal, the bit and bit bar is actually vertical. The cell actually has a tiny issue, which is the bulb. We need to bend the bulb. You can see that we are doing the bulb like this and this. So we need to bend the bulb. But there is another way of doing the layout, where we make sure that it is lithography friendly, where you don't bend the poly. So you can see the poly here, here, and here, and here. It's not bent. It's not bent. Now for the commercial SRAM, this is like to see what's going on with the RAM. This is one in 130 nanometer, 90 nanometer, 65 nanometer, 45 nanometer, and 32 nanometer. You can see that this is basically the same layout that we discussed before or that we discussed here. They're using that. And in the 65 nano, 40, the 65, the 45, and 32, they are using the one without bending the pole. We call this design the thin cell design. And as it's mentioned here, we transitions to thin cell at 65 nanometer. This is small pictures here where you are comparing feature size with the cell size, and you can see that it's actually linear. The relation is linear, and the slope is negative, where it is actually reduced within the feature size. So as newer generation in the memory, uh, we have every time a smaller feature size, and in terms, because the transistors are small now, we have a smaller cell size as well. Now, after we talked about the cell, we will talk about the other components of the array architecture, starting with the decoder. So the decoders, you know that it's actually n to 2 to the power of n decoder. So one of the famous ones is 4 to 2, or sorry, 2 to 4 decoder. The 2 to 4 decoder is actually like this. You have two in the input, 2 bits, and you are generating 4 outputs, where one of them will be hot, meaning that it is 1, and the other will be 0. It's based on the choice. Since we choose this one, if we say that this is 0, 1, 2, and 3, then the address that chose number 3 should be 1 and 1. That's the decoder. Now, for an n to the power of n decoder, it consists of 2 to the power of n input and gates. So it's basically the A and A0 and A1 representing the address, and you have n and gates. Since you have 2, the output should be 2 to the power of 2, which is 4, and you have 4 and gates. There are so many designs. This is 2 designs, the static CMOS design and the pseudo NMOS design. And both of them, you can see that we have an inverter followed by another inverter. This is again for protection. You want to protect what's inside the decoder. That's why we have those 2 inverters. You don't want the noise or leakage to affect the inside of the decoder. So here in word 0, it's connected actually to A0 bar. So that's A0 bar. And here it's connected to A1 bar. And you can see the layout here, or the block diagram, where you have in A0, one time it's inverted, one time is not. One time is inverted, one time is not. And for A1, 2 times inverted, 2 times is not. And this way we got word 0, word 1, word 2, and word 3. Now the design of this AND is done this way. We have the NAND followed by the inverter and the sizing as you can see. For the pseudo NMOS, same idea. The only thing is now we have a NOR circuit here of inverted input AND, meaning that this is a NOR. And the NOR in the pseudo NMOS is done this way, where you have one PMOS connected to the ground, always on, and you have two NMOSes in parallel. We add 2 inverters to make sure that you have a bigger fan out of the word, because this word is actually connected to many cells. So that's the idea of the decoder design. Now, that's a larger decoder where you have n larger than 4. So here actually we gave it the value 4. So we have A0, A1, A2, and A3, and we have 16 different words from word 0 to word 50. So the only thing here is now we have 4 input and associated with each output. And we can convert it to NAND, NAND, and NOR, NAND, and NOR, and so on for a smaller design. You can see how did we chose the inputs, where you have here for the A0, since it's the least significant bit, one time is inverted, one time is not inverted, not inverted, and so on. So let's say inverted, normal, or you could say it like the truth table, 0, 1, 0, 1, and so on. Here you have 0, 0, 1, 1, and so on. Here you have 4 zeros followed by 4 ones, and so on. Here you'll have 8 zeros. The slide is not enough to show you the whole thing. And then followed by 8 ones. That's for the large decoder. Now, the thing that you need to be aware of here is that there is actually a repetition of the NAND circuits. So here, actually, the same NAND in the red circles, we used it. It's the same one. We used it for word 0, we used it for word 1, word 2, and word 3. So why the repetition? We should have only one NAND for all these 4 words. Similarly, those blue circles, it's actually repeated. You can see that the inputs are the same. So it is repeated. Actually, even the other NANDs that I'm not highlighting, they are repeated, but they are repeated with other words that are not shown in the slide. So what we will do for all of the level 1 NAND circuits here, we will factor them out to make the decoder small. How? This way. So we will keep the NOR, same place. We will keep the NORs. They are here. And we will factor out all these NANDs. Now we need only for a 4 to 16 decoder. We need only 8 of them. 4 of them will be low 0, low 1, low 2, low 3, and 4 of them will be high 0, high 1, high 2, high 3. How is this happening? Now for these 4 NANDs, we will make it again, since A0 is the least significant bit, it would be 0, 1, 0, and 1. For A1, you will have 0, 0, and 1, 1. Now what we will do for the other NAND, we actually copy this and we paste it here. So it's exactly the same. Now how to distribute it, these NANDs to the other word or the other words in the output. We will have for the lows, the 4 lows 1, low 0, low 1, low 2, low 3. We will have it like this. So we will choose it for the first one for word 0, the second for word 1, the third for word 2, and this one for word 3. So they are nicely organized. And we repeat the same thing. We make it this way, and this way 4 times. From word 0 to word 3, and then from 4 to 7, and then from 8 to 11, and then from 12 to 15. We do it the same thing. And for the first 4 words, we choose this NAND in the high 0. The next 4, we will choose this one. And the next after this, we'll choose this one. And the last 4, we will choose this one indicated by this word 15. This is the organization. Now, this design, where we factor out these NANDs, is called the pre-decoding. The pre-decoding. It factors out the common gates into pre-decoders, saves the area, and it has the same path effort as the normal decoder. Now, for the column circuitry. The column circuitry is required for each column. You need actually the bit line conditioning, and we talked about it, and you need the column multiplexing. So we will start by the bit line conditioning. The bit line conditioning, the main job for it is pre-charging the bit line high before the reads. So you make sure that these 2 lines are 1 and 1, which is the first step of the read. Even it's a good preparation for correct. You could equalize the bit line to minimize the voltage differences when using sense amplifier by applying this or adding this PMOS. So if one of the lines having the value before the other, this will, when this is on, it will have the value moved into the other one as well. Now this is for the bit line conditioning. For the column multiplexing, we could do it using many methods. One of them is the 3 decoder mux, where, as you can see here, since you are choosing between 8 lines from B0 to B7, and you wanted to choose one of them, you could do a tree hierarchy, as you can see here, where you go down from 8 lines to only 1. Since you have 8 at the inputs, you need 3 multiplexing lines, which is A0, A1, A2. And as you can see in this design, we have for each input line, we have B0 and B0 bar, B1 and B1 bar, and so on. Similarly, for the selection, we have A0 and we have A0 bar, A1, A1 bar, A2, and A2, and so on. For example, let's pick up one of them. So 5. If we have this B5, the 5 in binary is 1, 0, and 1, meaning that this one will be chosen. So we will choose these 4. And for this one, you will also choose these 4. For the 0, meaning that this is off, and this is off, and this one is actually on, and this is on. For the 1, this will be on, and this will be on. So if you choose 1, 0, 1, for this example, the output that will be received by Y is actually B3. So you have, this is connected to this one, and this is connected here, and you get the output here as B3. So that's the code for having a B3, even though that at the beginning we're expecting that it's going to be B5. And similarly, you will have B3 bar here. If you want 101 to be B5, what you could do is actually replacing the B5 with the B3, but you need to make sure that everything is working correctly as well. Okay, so another way of doing the multiplexing by using a single pass gate multiplexer. We know that this is the decoder. So if we have 4 outputs in the decoder and you want to choose one of them, you could connect each one of them to an NMOS transistor, to the gate of the NMOS transistor. So if, for example, you have 1 here and 0 and 0, and 0 meaning you have a one line is chosen by the decoder, this NMOS will be on and the rest will be off, meaning that you will choose B2 at the output. And this is the way you do the multiplexing here. Now, remember when we did the architecture of the SRAM cell with the bit line conditioning and making sure that the read and write is working correctly? We did that here. And we said that we need to combine both of them together. Now it's time to combine both of them together. And we did it by the two-way mixed SRAM. You can see it's the same thing, only there is an organization. You have 2 columns, the left column and the right column. And the left column is chosen if you choose A0 and you make it 1. This one, or the right column, will be chosen if you have the A0 equal to 0, meaning this line. So these 2 will be on if you choose this one. If you want to choose this one, these 2 will be on. You have the circuitry below here to make sure that the write and read works correctly. So we will have both scenarios in the next 2 slides. This is the first one. This is for reading from the left column. So we choose the left column, and we want to read the cell there. To choose a cell from the left column, you have to access it by activating its word line. So we will activate this word line once we chose it. Also, to make sure that you are choosing the left column and not the right column, you make the value of A0 here equal to 1, and the A0 bar definitely will be 0. So this will be off and this will be off. Since we are interested in the read operation, both the right 0 and right 1, both of them will be, those transistors will be 0. So they will be off. Now, as you can see here, the phi 2, when the phi 2 is active, this line will be 1, 1, and this line will be 1, 1. And also here, it will be connected to the VDD. So this line here will be 1. So it will be 1 here and also here. But since we are not choosing the right column, doesn't mean anything because both of these transistors are off. But this one will be 1. So it's 1 from the top, also from the bottom, because there is this transistor that we make it a 1 for this case, and we chose this cell. Now what happens is, since we are reading, we size the cell to make sure that the read and the write works fine. And this way, we will have one of these lines flip to 0. When phi 2 is charging, it will be 1, 1. One of them will be 0 based on the value inside this. So we will have one of them going here and actually nowhere because it doesn't have access outside. But this one here will go outside through the inverter and you can read the data outside. This is the read operation. Now for the write, what happens is now, since we are writing to the left column, you choose the word line and you assign 1 and 0 as we mentioned in the read. And this way you choose this cell, actually this cell from the left column. Now to write a value, you assign write 0 and write 1 the way you like. If you assign it 1 and 0, then you will write a value. If you assign it 0 and 1, then you will write the opposite value. In this case, the value that the value that we chose is 1 and 0. If that's 1 and 0, what's happening is this 0 or the ground value here will be connected to this line. So originally it was 1, 1, 1, and now this one will be 0. If it was the other way around, the other one here will be 0. Since this is 0 and 1, you will write the value here 0 and 1, and it will work because of what we described before. And this way we combine both of them, the read and write. There are many ways to do this, and you can read the book for better ways actually. Now we will talk about the other subject that we need to focus on in this slide. The main actually part that we needed to talk about is already covered, which is the SRAM. And we covered it with all of its components. Now we will just talk quickly about the serial access memory. The serial access memory do not use an address like the shift registers, the tab delay lines, CPO, PISO, and the queues, which is FIFO and LEAP. The shift register is like what you see here. You have basically flip-flops with the same clock, and you have an input and an output, and you have it serial. Each clock, you will have a serial input coming inside the shift register, and it's serially will go to the output. So it's actually serial in, serial out. The shift register is actually serial in, serial out. For the serial in, parallel out, here you have a serial input, but you have a parallel out. So you read 4 bits of the same block. So we have here the parallel in serial out. So now the inputs could be fed to the registers or the flip-flops in memory. So you have B0, B1, B2, and B3. You have a mux before each one of the registers because if you want to load, you will choose this value to be 0. So you load the value, B0, B1, and B2, and B3, and becomes stored inside the flip-flop after you give it 1 clock cycle. And then after this, you change this value to 1, and now you will shift. You will shift the result into the output. Every time you have a clock, you will shift 0 inside, as you can see indicated by this value. So you have a 0 and you shift them out into the output. Now for the queues allow the data to be read and written at different rates. The read and write, or you read and write each use their own clock and data. So sometimes the read has a clock and the write has a different clock, and sometimes we have the same. The queue indicates whether it is empty and or full by certain indications, like this one. You have empty and full, and you have a write clock and read clock, as we said before. And you have the data. You can write the data inside the queue or read them from the queue. Built with SRAM, and the read or write were counters or pointers. Now the operation that you use with the queue, the first, or before I talk about this, let's have the first type, which is the FIFO, the first and first line. The two operations is InQ and DQ, and we have the LIFO or the stack, and the operations here are push and pop. In the FIFO, you initialize the read and write pointers. So you have 2 pointers to the first element. So originally, because you initialize them at the beginning in the first element, the queue will be empty. This way, we know the queue is empty. On write, you increment the write pointer. On read, you increment the read pointer. If the write almost catch the read pointer, then the queue is full. For the LIFO, the last and first out, is also called a stack. We have the push and pop operation, and we use a single stack at the top of this stack. This is called a stack pointer, and we use the same pointer for read and write. This way we finish the talk of today, and next time we will talk about the stability.